So we're jumping in and learning some more calculus. We have just finished the first section in our textbook, which covered average rate of change, instantaneous rate of change, or just rate of change. It doesn't have that average in front of it. And then find at a particular value, and then finding the equations of a tangent line. Sorry, something came across my screen that I had to read. So today we're going to move away from that, except I'm going to go over one problem first. We're going to move away from that, and we're going to look at the concept of what it means to be a limit, and taking a limit as x approaches a value of a function. And you're probably, if you haven't had calculus before, wondering what I'm talking about. But by the end of this class period, you should be know what I'm talking about. So let me jump in, share my screen. This next problem that we're looking at, or this first problem that we are looking at right now, is one of your homework problems. And it's looking at the graph. And looking at the graph, the first part of the question, and I'm not doing any of those, was finding the average rate of change over a certain interval. So that's where you're going to look at your 2 points and you're going to take the slope of that. But as you work down through the parts, you'll find that it's going to ask you for the instantaneous rate of change at a particular value, or in this case, hour. So the following graph shows the total distance traveled by a bicyclist after T hours. And so we have hours here on the horizontal, and we have the distance traveled here on the vertical axis. And so we want to find the instantaneous rate of change of the bicyclist at T equals 3 hours. And so I'm looking at that over here when we have T equals 3. And so I want to know what that instantaneous rate of change is there. And so to help me, I'm just going to grab my ruler, if I can find it. And I'm going to make it go through this point. And what I would think that looks like, I can do it, which looks like a point on my graph. So I have my 1 point when T is 3. And I can see when T equals 3 here, right? That my value here for S, my Y value is going to be 18. My intervals are going up by 2. And so I know I have a point at when T is 3, the distance is 18. And I want to find another point. And so because I made it look like the tangent line going through that point at T equals 3, I'm going to just choose a point to me that I recognize where it is. And so doing that, how about let's choose this point right here. Okay, so this point right here on my graph, well, that would be when T is 3.5. My Y value there is 22. The only reason why I chose that point was because that point looked like it fell on my tangent line. And it was something that was also on this. It didn't really actually have to be on that function itself. So we're just finding the slope. So we're finding the rate of change of our Y value, or in this case, the distance, which was S. So looking at 22 minus 18, all over the change in time in this case, which is 3.5 minus 3. So simplifying, I get 22 minus 18 is 4, all divided by 0.5, which is equal to 8. Okay, so this is an estimate, right? We're trying to, by looking at the graph. So if I was looking at the values or my answers, well, 8, it looks like A is the most accurate. or 7 miles per hour. Just looking at this, you should be able to exclude some of your answers, right? Slope talks about, how fast we're rising or falling. And if our slope is positive, moving on the graph left to right, we know our slope has to be positive. I know this is increasing at this value. So right away, we could just eliminate it being negative values in this example. So let me see if there's any questions on that. And if not, we will move into limits. Pause the video for a second. Okay, so great questions from the students, and I wanted to turn back on the recording and kind of talk about this and what you guys were asking. And so notice that my answer here of 8 miles per hour was not one of the choices. And so we are estimating, and so you might, you're just going to have to look at all of your choices and use the best answer. It's hard because we're looking at the graph and we don't have the function. And so we can't be plugging in points as we get really, really close to 3. And then another question was, did I have to choose the point where I chose it to find the slope between those 2 points? And I didn't. I just tried to choose something to me that looked like it fell on this line in here. That would look like my tangent line. And I was trying to choose something that was going through part of the corner of one of those grids. And so for instance, here, if I had chosen here when t was 2.5, my answer should be pretty close. So I could have looked at 318 and 2.5. And if time was 2.5, then my y value is 14. And so if I plug this into my slope down here, and then I would get 18 minus 14 all over 3 minus 2.5. And again, I'm getting about 8 here. And that's just how I thought my line looks as a tangent line on that graph itself. So I get 4 over 0.5, which is 8. Which was not one of my choices, but it's pretty close. And the other answers just don't work. And I don't believe I stated this, but you can see this X with the video on of -18 and -22. And I was talking to the students that are here saying, we should know that those aren't part of our answers because we're talking about finding the slope, that instantaneous rate of change at a particular value. If you look at the graph slope, we're increasing on this function, and we know if our function is increasing, our slope is greater than 0. If our slope is negative, then our function would be increasing. So m greater than 0, we know it's increasing. And then if our slope was less than 0, we know our function has to be decreasing, going down from left to right. So let's move on.
Awesome.
So, okay, we're going to look at limits now, and limits is one of a big concept in calculus, and we'll get back to looking at instantaneous rate of change a little bit later in this chapter. But for now, let's look at what it means to be a limit and what we're doing as we're finding limits. And I looked in, we talked about a little bit of this notation a little bit earlier and this week. So let me start on that. So in front of us, we have the definition of a limit. And it states that we say that the limit of f of x as is L as x approaches A is written as the following. Okay, so underneath this LIM limit, you'll see an X with an arrow going to A of f of X, and then it's equal to capital L. And so that's what that notation is saying. And we say that this limit as X approaches A of f of X equals L, provided we can make f of X as close to L as we want for all X sufficiently close to A, from both sides without actually letting x equals a. Okay. So let's discuss exactly what that's talking about. And we're going to get into, and this is more like the formal definition of a limit, and we'll get more into that next section. But for now, we want to look more at the intuitively what is going on when we're saying this. And so let's look at the following graph. So right here, I have some graph. And it's actually the graph of f of x equals x squared minus 1 all over x minus 1. A lot of times, if we're doing limits, it depends. Do we have the function or do we have the picture of the graph? If I wanted to look here at the limit, let's say as x is approaching positive 1 of my function f of x, which is x squared minus 1 all over x minus 1. The first thing that you always want to do when you're looking at finding a limit of a function at a particular value is just do direct substitution. So all we're going to do in here, we're going to plug in 1 wherever we see an x in this function. And so let's do that. And doing that, so I'm first going to just go in here and I'm going to put parentheses wherever I see an x. So I'm going to have, I see an x, I'm going to square that value minus 1 all over, I see an x down here, minus 1. So let's go in, wherever we saw an x, we're plugging in 1. Well, if I simplify this, this gives me 1 minus 1, 1 squared is 1. 1 minus 1 is 0, all over 1 minus 1, which is 0. So you're going to hear this a lot in this course. When we get something in the form of 0 over 0, this is called an indeterminate form. So note, 0 over 0 is an indeterminate form. And when we get something in the form of 0 over 0, or there's other forms that are indeterminate, it doesn't tell us anything that we're trying to look for. And so this tells me that I need to go about and manipulate this so I could figure out the answer. And so we need to do some more work. And so I'll be giving you some tricks the next few weeks on what to do if we get this indeterminate form. Well, one trick is to factor. And so let's look back at our function. So limit as x is approaching 1 of x squared minus 1. Let me just write it down here, all over x minus 1. So I notice that I can factor my numerator here. I have a difference of squares in my numerator. If I'm getting 0 over 0, that's meaning that we have factors that are in common in this case. And so I can rewrite this as x minus 1 all times x plus 1 all over my denominator of x minus 1. So we have a stipulation for our function. We know for this function, we can't have any value of x which sets our denominator equal to 0. And so we know that in this case for f of x, x can never be 0. I'm sorry, not 0. X cannot be 1. That's what sets my denominator equal to 0. So if I go in here to this function, f of x, and I simplify it though, we get back that really f of x is equal to x plus 1, with the stipulation that x can't be 1. And really, when x is a 1, if I plug in 1 here to this new function I had, just of x plus 1, then I would have a value of 2. So at that 0.12, there's a hole in the graph. Right, so that's why technically we have this hole in the graph. And then notice that function now of f of x equals x plus 1. That's just a linear, that's a line, that's linear. It's in the point slope formula. I'm sorry, slope intercept form. And so we can tell, you know what, and you should be able to graph lines pretty fast. We should tell that that y-intercept is b, that our slope is 1. So if we rise 1, go over 1, rise 1, it's just a line. Okay. Let's go back because we simplified this, right? If I simplified this limit right here, and I canceled out like factors, this is the same thing as the limit as x approaches 1 of this function x plus 1. Oops. After simplifying. And so now if I look at this limit as x is approaching 1 of the function x plus 1, and I just went in and I did my direct substitution, notice that wherever I see an x, I'm going to plug in 1. I get back a number. I don't get that indeterminate form anymore. I get that back, that number of 2. So what that tells me then is the limit as x approaches 1 of my original function x squared minus 1 all over x minus 1. This is equal to 2. So this is what I would have done if I was just given the equation, but I also want to look at this as if we were given the graph. So limits, you're always looking at approaching some x value, and we're technically looking at what is that, as we approach that x value, what is happening to our y value. So let's look at that picture again. I want to see if I can grab it and paste it. Let's do this. So let's look at that picture. Oops. And talk about it graphically. So when you're looking at limits graphically, and we, in this case, again, we want to look at the limit as x is approaching 1. You want to see what is happening to your y value as x gets closer and closer to 1, maybe not particularly at x equals 1 itself. And so what we're going to do as I look at where my value is that I'm trying to find where my limit is approaching, in this case at x equals 1, and then I look at what's happening to my graph as I come in to that x value of x equals 1 from both the left and the right hand side. And I want to see, is it going to one particular number or not? And it has to be coming into the same value on the left and the right in order for a limit to exist. And so notice, even though we have this open circle in here, my value on the left, that is getting closer and closer to a y value of 2 as I get closer and closer to this x value of 1. And if I'm coming in on the other side, the right-hand side, as I get closer to x equals 1, my y value is getting closer and closer to 2. And so by looking at the graph, this is equal to 2. And I'm going to just put in this case, even though one, 2 is not a point on the graph. or on the curve. Okay, so first locate the value you're looking for the limit at. Your X value, look at where the graph is around that area and see, are we coming into the same Y value as we follow that graph in the left and the right of that X value we're looking at. So kind of talk about it again really quickly because this is a big concept and sometimes students get confused with this. So at X equals 1, right? I could choose a value of, 0.8. If I plugged in 0.8 into my function, I would get back 1.8. So, right, if I have X, f of X, even if I plugged it back in here, and I plugged in 0.8, that's close to 1. And I get back my value, right, of 1.8. If I plug in 0.9, you'll see on the graph that we have 1.9. If I plug in 0.99, right, I get 1.99. So as I'm getting closer and closer to this value, my Y value is getting closer and closer to 2 on the left. And same sort of idea, like if I put in 2.1, that's close to 2 on the, I'm sorry, not 2.1. If I put in 1.1, that's a number that's close to 2, I'm sorry, not 2, 1 on the right. So 1.1 plus 1, so this would be 2.1. But as I get closer and closer to this value on the right of 1, so 1.01, my value of Y is getting closer and closer to that value of 2. So since we're coming into the same value on the left and the right on that graph, our limit is 2. So I wanted to show you a couple of other examples that are similar to this problem, but a little different. So let me pause for a second to see if there's any questions. Okay, so great question. And it talked about how in our original function, we had put in that X could not be 1, and that was because it set our denominator equal to 0. And why were we not plugging, or why were we plugging in values that were close to 1, but not 1 itself? And how could we do that? When we are taking limits, we might not actually worry about what's happening at that one value that we're taking the limit for. What we're worried about, or what we're wanting to know, is what's going on around that value that we're looking at the limit as X approaches. And so when we're looking at what's going on around this X equals 1, we want to know, and we want to know what's going on with the Y value. We want to know, is it getting closer and closer to something, or is it going off to infinity, or is it undefined? I mean, you might have positive or negative infinity there. And so we're not really, sometimes we don't worry that that value is undefined there. We're worried about, for limits, what's going on. Is it approaching the same value on the left and the right? I hope that through that helped. Like, so for instance, I was saying, let's look at another example that's very similar to what we just did. So notice this graph is almost identical to what we had just had. They just then put in a stipulation, and they said, okay, we have a piecewise function here. G of X is equal to first equation, the same one we had before, X squared minus 1, that quantity all over X minus 1. They put here, that's going to be the equation we're going to use for all values of X, as long as X isn't 1. And then they said, okay, when X equals 1, let's define it at a point, a Y value of 1. And so that's why we have this point on the graph down in here. In this case, we want to see still what's happening as if we were looking at the limit, as x is approaching 1 of this g of x function. And so I'm really just concerned on the graph when x is 1, if I come up here and I go to the piece of the graph to the left of x equals 1, and I follow the graph up here as I get closer and closer to 1, but not 1 itself, I want to know, is that y value approaching 1 number? And so again, I can see in this case, as x is approaching 1 on the left, and let me just give you that notation. So limits as x approaches a number on the left, we're gonna write this, so we don't have to just state this, as a limit as x approaches some value. I'm just gonna put 1 in here. On the left, we're gonna put what looks like an exponent of a negative number. And so that's how we're gonna write that in this case of g of x. And so I can see here that the limit as x is approaching 1 on the left, the y value that I'm getting closer and closer to, but not equal to, is equal to 2. If I'm looking at it, limit as x approaches a number on the right, how we're going to write this out is again LIM for limit, an x with an arrow, and then we're coming in on the right hand side. So instead of the exponent looking symbol, instead of it being a negative, it's going to be a positive. And that's how we would write that piece. So I want to do the same thing. I want to look at the limit as x is approaching this number up here, 1, but I want to see what's going on as I'm coming in on the right hand side. So is it still coming into that same y value? So even though there's an open circle here and I'm not getting back that 2 value, I'm getting really, really close to that 2 value as I get closer and closer to this 1. I'm just going to write it down. A limit exists if the limit as x approaches a value, a of f of x, on the left is equal to the limit as x approaches some value of x, let's just call it a, on the right. If that's the case, let's say that it was equal to some number L. That was our y value. Then we can say then the limit as x approaches a in general of our function f of x is equal to L. So sometimes we're only worried about what's going on one side of our limit versus another, but then also sometimes we're worrying what's going on the left and the right of that x value as we're looking at the limit. So let me see if there's questions. So basically this is the almost identical graph. This time we have each of x is equal to x plus 1. And notice that we have a solid circle there. And it's so at that point is actually defined and falls on that line. And so same idea, if I looked at the limit as x is approaching 1 of x plus 1, Notice our y value as we come in from the left and the right, our y value we get back is 2. And I could see that if I did direct substitution and I plugged in 1 here and here, wherever I saw an x, I would see that that's 2. So let me pull up a couple other examples. Okay, so let's look at some more examples of just finding limits by looking at a graph of some function. So looking at this graph, I can see that this function, and it is a function, right? Because it passes at vertical line test, is actually a piecewise function. So there's multiple different equations based off of which piece I'm looking at. But anyways, let's say that we wanted to look at the limit as x approaches -2 of this function. And actually, I'm not going to say x because I look at that up here and it has s equals f of t. So I'm going to use the variable t instead. So t is approaching -2 of f of t. So again, all you're going to do on the graph is you're going to locate the value that you're looking at the limit. In our case, it's t equals -2. And you're going to go to the left and the right of this around that value that we're looking at. So, and see, are we coming into the same y value as we come up on the, in this case, up on the left of the graph of -2? And so notice that even though there's an open circle here and it's undefined at x equals negative or t equals -2, my y value or s value in this case that I'm getting back looks like it's 0. So here, as we're coming into -2 on the left and the right, this value that we get back is 0. If I wanted to look at, let's say, the limit as t approaches -1 of f of t. So I would look at this, I would locate where my t value is, in this case of -1. I would come down to my graph and see where it's located and what's going on as I follow the graph on the left of -1 and the right of -1. Is it coming to the same exact y value? And in this case, it is. My y value that this is approaching, coming in on the left and the right, would be back -1. So if we're talking about this, though, as the limit as t approaches 0. So if we come back to this graph and I look at when t is 0, notice that coming in on the left of t equals 0, I'm getting a y value down here of -1. But if I'm coming in on the right-hand side of t equals 0, I'm getting a y value that's getting closer and closer to 1. And so because of that, the limit as t approaches 0 of f of t does not exist. I'm going to write down what I had just said before. And that's because the limit as t approaches 0 from the left-hand side, so 0 with that exponent-like negative from on the 0 of f of t is equal to, so the y value when we're getting closer and closer to 0 is -1, which does not equal the limit as t approaches 0 on the right-hand side of f of t. That's equal to +1. So left and right don't equal to each other, then it doesn't exist. But we can have the limit exist on the left and the limit exist on the right, with the limit not existing just altogether. So let me just ask you a couple more questions about this graph, and that will be helpful, and it's just kind of a review. So let's say that we wanted to find, I'm gonna put D up here. And our function's name is f of t. So let's say we wanted to find f of 0. All that's telling me is my t value is 0, and that's asking me what is my y value when t is 0. So because I have an open circle up here, that's not defined at that point. Open circle is not defined at this point, but I have a solid circle here. And so if I was evaluating what f of 0 was, this would be equal to 0. If I asked what f of -2 is, so this is saying when t is -2, what is our s value? What is our y value there? S really, but I like to call it y. Notice there's only an open circle there. There's no point that falls above or below this t equals -2. And so in this case, notice that this is undefined. So it's possible that something is undefined at a point, but we saw that our limit did exist. So if I ask one more question, what is f of 1? So look at when x, not xt in this case, is 1. What is our y value there? Well, it's on that line, and so our y value is 1. So just a little bit of review of that function notation and what you're talking about when you're looking at graphs. So like I had mentioned when the video was off, we did not finish this section on limits and their graphs. We're maybe like halfway through, but we still have so many properties. We need to look at properties of limits, and that's going to help us be able to find them. And so we will continue on this topic in next week's class.